Okay, good morning all of you. Any questions from yesterday's class? Any questions from yesterday's class? And as we go to 3D or space frame analysis, you should be familiar with vector algebra. Okay. So anyway, I will show you an example, so then you will understand what is the importance of this vector algebra for this space frame analysis. So this is a space frame. Yesterday we discussed about this, not in complete sense, but we started discussing about this. This is a frame element which is coming out of the plane of this board, okay? And local x-axis, y-axis, z-axis are all shown here. And the load application is also shown. Transverse load is applied along two different planes, along xy plane and also xz plane. And for space frame, if you take a two-node element, two-node space frame element, at each node you are going to have 3 translations and 3 rotations. So total 6 degrees of freedom at each node. So total degrees of freedom are going to be 12. So please take a note of this if you have not done it. I'm not getting any response from student side, so I hope everything is clear. So here space frame element, the element equations can be obtained by combining the axial effects, bending effects along two planes, and also torsional effects. Yesterday I showed you the differential equation for an element, structural element undergoing torsion. Okay. What is the governing differential equation? That equation looks similar to this two-node bar element undergoing axial deformation. So wherever E, A are there, you need to replace with GJ, and wherever U is there, you need to replace with theta. Okay. Anyway, once again we'll go through it. So this is a space frame element in the local coordinate system. And these are the various degrees of freedom. And also other quantities, forces, moments, and the moment, because it's undergoing bending in two planes, xy plane and xz plane, you require to know what is moment of inertia of cross section about y-axis, local y-axis, and z-axis. In a way, you need to know moment of inertia about minor axis as well as major axis. Even though here the section is shown to be I section, you can have different shapes of sections. And now this is these are the forces and moments. Okay. Again, even how this force Fx is related to moment mx by right hand thumb rule. Yesterday I showed you what is right hand thumb rule. You point your thumb, your right hand thumb in the direction in which this arrow is showing here for Fx, and the direction in which your other fingers are going to curl, that is going to be the direction in which this moment is going to act. Double-headed arrow is shown for moments. the meaning of this double-headed arrow is moment, but the way it is acting, to get a feel for it, you need to use right-hand thumb rule with thumb pointing in the direction in which fx is acting. Similarly, thumb pointing in the direction fz is acting for mz, and thumb pointing fy for my. Okay. So for axial effects, this is the element equations, and here once again, whatever element equations we are deriving or whatever analysis we are going to perform on these space frames, that is based on the assumption that axial effects, bending effects, and torsional effects are uncoupled. Axial effects, bending effects, and torsional effects are uncoupled in the sense this space frame element is undergoing small deformations, so that we can ignore the interaction effects. Axial effects are not going to affect or are not going to have any effect on bending, or they are not going to have any effect on torsion. Okay. Similarly, other things. So axial effects, the equations, element equations with corresponding, you can see here, corresponding degrees of freedom and corresponding forces. And bending effects along xy plane. And also you need to go back and sign conventions, you need to follow whatever sign conventions we noted, okay, for internal moments and shears and also axial forces. All that is those sign conventions you need to carry forward, because we are using same element equations as that we used for beam element. So this is bending effects because of the flexure in xy plane, and bending effects due to the bending effects for forces in xz plane. They are shown here. Okay, and this is how you are going to interpolate your transverse displacement. And all these you are familiar with. If you had already solved beam problems, these are all familiar to you. So this is bending effects in xz plane, and this is your force vector, the equivalent nodal forces due to the applied uniformly distributed load. And one more effect, torsional effect, and this is the relation. Moment is related to twisting moment to angle of twist, how they are related. This is similar to if you see the corresponding equation for a bar element. For a bar element, instead of M, you are going to have force F. Instead of GJ, you are going to have EA. And instead of theta, you are going to have U. Okay? In a way, for bar element, it's going to be force equal to Young's modulus times area of cross section times strain. Similarly, moment here for a element which is undergoing torsion, twisting moment is given by GJ, which is nothing but your torsional, here it is written torsional stiffness. Torsional stiffness multiplied by the derivative of angle of twist. It is similar to your strain for bar element. Okay, so this is how moment is related. What is the governing differential equation? I explained to you in yesterday's class. And this torsional constant J is there, which is torsional constant. It depends on the cross-sectional properties. For different cross-section, what is that is given here. for few of the cross sections. And if you refer any standard textbook on strength of materials or mechanics of materials, or any this handbook related to design, you can find these torsional constants for various cross sections, even for T section and all kinds of sections. Okay. And what is the governing differential equation? This is the governing differential equation. Yesterday I explained it. I also explained the similarity between this equation and whatever governing differential equation we get for a bar element or a truss element undergoing axial deformation. And once you have that understanding, you already noted the element equations for axial effects here. Element equation for axial effect. If you want for torsional effects, wherever E is there, replace with G, and wherever A is there, replace with J, and corresponding degrees of freedom and corresponding moments. So this is the element equations for torsional effects. So now you have all the element equations for axial effects, for bending effects, for torsional effects. And now, with the assumption that all these effects are uncoupled, we can write the element equations for space frame element. And the size of this equation is going to be 12 by 12, because 12 degrees of freedom are there, and corresponding forces, and depending on the degree of freedom, it can be force or it can be moment. And please note that this is the element equation, the local coordinate system, small x, small y, small z. And you can easily, with the explanation that I gave you for plane frame, you just follow that. You can cross check whether the contributions are placed at the proper location or not. From axial effects, from bending effects along two planes, and torsional effects, whether they are placed in appropriate location or not, please cross check it. Okay, any questions here? So this is about a space frame element. And if this space frame element orientation is different from the global coordinate system, then we need to apply whatever we learned so far. Similar to that, we need to find transformation matrix to get this stiffness matrix. In the global coordinate system, you need to multiply transformation matrix transpose of T transpose KL T, transpose of transformation matrix times this stiffness matrix 12 by 12 times transformation matrix. And transformation matrix is also going to be 12 by 12. Transformation matrix is also going to be 12 by 12, and transformation matrix is going to be orthogonal matrix. So now we need to focus on how to get this transformation matrix. How this transformation matrix is going to look like. This is how it's going to look like. For displacements, local displacements are going to be related to global displacements via this transformation matrix. And this relation is similar to trusses or plane frames, whatever we have seen. This equation is going to be same, except that dimension of this DL is going to be different here. Dimension of D is going to be different, and T is 12 by 12. You can see here T is 12 by 12. R is here 3 by 3. So you can see 3 by 3, 3 by 3, 3 by 3, 3 by 3. So 12 by 12. And it's going to be diagonal matrix. Diagonal in the sense it's going to be banded kind of thing. Okay. And this T is going to be orthogonal matrix. Still, it's not clear at this stage what this R looks like. What this R looks like, it's not clear. We will see how it does look like, how it has to be calculated. And you already know what are the direction cosines for plane frames, and also this space truss and plane truss. You used direction cosines, Lx, Mx, Nx, and here we need to also make use of Ly, My, Ny, Lz, Mz, Nz. We'll see how to calculate all that. And this figure is showing the degrees of freedom for this element, space frame element, in the global coordinate system. In the global coordinate system, what are the degrees of freedom? In the local coordinate system, we used D1 to D12, and here we are using this kind of notation because we are looking in the global coordinate system. Please take a note of this. The important thing is how to get this, whatever is written here, rotational matrix or rotation matrix. How to get this rotation matrix? That is what is important. And that is what is new thing that you are going to learn as a part of this space frame analysis. For calculating this rotation matrix, you require to refresh or recap your vector algebra. Okay. So these are the direction cosines. Local coordinate system is related to global coordinate system via this direction cosines. And this relation, anyway, you already noted when you looked at space truss element, and still it is not clear. We will see how to calculate this. We know how to calculate Lx, Mx, Nx. And only thing is here you also require Ly, My, Ny, Lz, Mz, Nz. How to calculate this we will see once we see a numerical example. Okay. Assuming that you know all this, you know this rotation matrix. If you know rotation matrix, you know transformation matrix. And you can find the stiffness matrix in the global coordinate system by doing T transpose KLT. And then you can assemble the element equations and then get the global equation system if it is required, or you can directly write the reduced equation system depending on which degrees of freedom are fixed or which degrees of freedom are zero. I should not say fixed. Which degrees of freedom are zero, eliminating those corresponding rows and columns, you can get the reduced equation system. Once you get reduced equation system, you solve for the unknown nodal degrees of freedom. And then once you solve for the unknown nodal degrees of freedom, you again make use of this relation. You get the local degrees of freedom. Once you have the local degrees of freedom, you can calculate all the quantities, axial forces, shear, because this is space frame, shear about y-axis, shear about z-axis, and torsional moment about y-axis, moment about x-axis, and corresponding fixed end corrections you need to apply. Corresponding fixed end corrections you need to apply for moments as well as shear wherever applicable. Please note that torsional moment is not required. For torsional moment, you don't need to require to apply this fixed end correction, because torsional moment is not distributed along the length of the member. Okay, so unless you solve a problem, all these making use of all these relations, it will not be clear to you. So a numerical example is illustrated here. This gives you complete picture how to solve a space frame problem. At the same time, to avoid too much complication, here simple space frame is taken. You can see here it consists of 3 elements, one element, or one element here, one element, another element. All the elements are joined together. All the elements, this is the common point for all the elements. Or the nodes are numbered like this: 1, 2, 3, 4. So this fourth node is the common node for all the elements. And what about this other node for all the elements? That is that is connected to the support. That is connected to the support. This is one support, another support, another support. And all the dimensions are given. FPS units are used. Material properties are given. Okay, and sectional properties are also given for you to calculate. Whatever torsional constant. To calculate torsional constant, you require to know the these dimensions of the section. Any questions here? Any questions? So now, now you need to go to each element. Okay, and you can see here. What I suggest is you please take a note of this. Okay, if you just listen to this like any Rama and Mahabharata like that, it will not be of much use. So please take a note of this. And here for each of the element, how the local axis is oriented, that is shown here. That is what we need to focus. That is what the new thing that you are going to learn. So local x-axis for this element is 1, this element is 2, this element is 3. So element 1 is connecting nodes 1 and 4. Element 2 is connecting nodes 2 and 4. Element 3 is connecting nodes 3 and 4. We need to also clearly make a note what is going to be the locally, what is node 1 for each of these elements, what is node 2 for each of these elements. Okay, and you can see here for element 1, the local coordinate system is shown in this manner. Local coordinate system, here it is starting here x and is pointing along this direction. That is positive x-axis, small x-axis, and small y-axis positive in the downward direction, small z-axis positive in the direction which is shown. Okay. Any questions here? So now we need to find what is the orientation of this small x, small y, small z, if the nodal coordinates are given. For that, there is we need to make use of our vector algebra. We'll see that. Similarly, for element 2, for element 3, local coordinate system is noted. Whereas the global coordinate system is this. Global coordinate system is this, and here it is shown. Global coordinate system origin is coinciding with node 1. Origin is coinciding with node 1. I hope you have taken note of this, because to understand further, you need to make a note at least for one element. Let's understand the procedure for taking for element 1. So for element 1, you please take a note of this coordinate, this local coordinates system. So now I hope you have taken. And now let's go to each of the elements. Okay, And before that, all the cross-sectional dimension, geometric dimensions are given, and also the geometric dimensions like depth and thickness, all those, that information is given. So you can find torsional constant. You can cross-check all this, whether these are correct or not. Okay, please don't accept whatever is written. Please cross-check by checking whether this torsional constant is correct or not. And once you have all this, we have defined some coefficients like this: A1, A2, A3, A4, and then this in the local coordinate system. In the local coordinate system, I can easily write what is the stiffness matrix for element 1. Or for if all elements are of same size. Let's see whether all elements are of same size. So all elements are of same size. So irrespective of whatever element you have here, element 1, element 2, element 3, cross-sectional dimensions are same, material properties are same, length of the members are same. So in the local coordinate system, the element equations are going to be same. Since all elements are identical, local stiffness matrix is same for all elements, and that is what this is. And now going to each of the elements. Going to each of the element. Please note that I told you, I emphasized enough on this local coordinate system for each of the element to actually determine this local coordinate system. What I mean determining the local coordinate system is, I need to identify what is the vector, what is unit vector along this small x-axis, unit vector along small y-axis, unit vector along small z-axis. That unit vector itself is going to be your direction cosines. Okay? Unit vector, components of that unit vector are going to be your direction cosines. So unit vector along small x-axis, unit vector along small y-axis, unit vector along small z-axis. To get that unit vector, we need to identify for each of the element, to identify that these unit vectors, we need to identify for each of the element a third node. A third node we need to identify. What is the third node? That is what is written here. What I suggest is you need to make a note of it, because I cannot, when I flip over these slides, it will be difficult for you to follow. So please take a note of this. So that is what is written here. The local axis for each element are shown in figure, whatever figure I showed you, local axes are shown. These local axes will be computed using this kind of understanding of nodes. One more node you need to identify. That has nothing to do with your later analysis. That is only to identify the unit vector along small x-axis, small y-axis, small z-axis for each of the elements. So please take a note of this. For element 1, node 1 is global node 1, node 2 is global node 4. That is what we have, we know that. For all the elements, second node is the common node. Common node is 4. So second node is that common node. And in addition to that, one more node is identified. You please take a note of it. Then we go to the figure. Then you will understand what is this. So for element 1, node 1 is taken as global node 1. Node 2 is taken as global node 4. Node 3 is taken as 2. Global node 2. Okay. So I hope you have taken note of this. If you have taken note of it, let's focus on element 1. For element 1, node 1 is 1. Node 2 is 4. Node 3 is 2. So let's see the figure. So this is element 1. For element 1, this is node 1, this is node 2, and in node 3, only for calculating unit vectors along small x-axis, small y-axis, small z-axis, this is identified as node 2. Sorry, this is identified as node 3. Okay, this is identified as node 3. What is the use of it? We will see in a while. Okay. Similarly, for other elements, second element, this is identified as node 1, node 2, and this is identified as node 3. You can see node 3. And for third element, this is identified as node 1, node 2, and this is node 3. Okay, so we'll see what is the need for it. So since you can read this, since since one node of each element is fixed, only matrices associated with degrees of freedom at node 4 are given below. Anyway, this is a separate thing. So now let's go to element 1. What is node 1? First node. What is second node? What is third node? You make a note of it. You make a note of all the coordinates. This is space frame. So at each node you have 3 coordinates. What is x1, y1, z1, x2, y2, z2, x3, y3, z3. You make a note of it. And please note that when we say here 1, 2, 3, these are in the local coordinate system. This is local node 1, local node 2, local node 3. That you need to keep in mind. And now, if I want Lx, Mx, Nx, Lx, Mx, Nx is nothing but unit vector along the local x-axis. Unit vector along local x-axis. How do I get unit vector along local x-axis? I know the coordinate of this node, node 1. I know the coordinate of this node 2, which is node 4. So I can find the difference in the coordinates, x2 minus x1, y2 minus y1, z2 minus z1, and divide with the length of the member. I'm going to get unit vector along small x-axis. That is nothing but components of that is nothing but Lx, Mx, Nx. This is what you are doing. This is what you are doing for plane frame and also space frame. Sorry, plane truss and space truss. This is what you are doing. Okay. Any questions here? But now we need to also identify unit vector along y-axis, unit vector along z-axis. How do I get unit vector along y-axis? How do I get unit vector along y-axis? You please take a note of this. Please take a note of this one. What is the meaning of that? I'm going to explain. Please take a note of this. So after taking note of it, just listen to me. When you are taken x2 minus x1, y2 minus y1, z2 minus z1, what you are getting? You are getting the components of a vector which is pointing in the local x-axis direction. You are getting components of a vector which are pointing in the local x-axis direction. And if you normalize it with the length of that vector, you are going. That is what normalizing is. This one, dividing with L is normalizing. If you normalize it, you are going to get unit vector. So that is how you got the These are nothing but Lx, Mx, Nx are nothing but the unit vector components in the direction of local x-axis. Now I am interested in what is unit vector pointing in the local y-axis. How do I get it? You see here, local y-axis is pointing like this. Local y-axis is pointing like this. Okay? So now I got this vector. And if I take this, a vector pointing in this direction, a vector pointing in this, how do I get vector pointing in this direction? How do I get vector pointing in this direction? I need to take this node or this vector pointing in this direction is going to be same as vector pointing in here. If I put this coordinate system here, it's going to be vector pointing in this direction. How do you get this vector z pointing in the direction? Vector z is pointing in the direction of this element. That is the reason this node is taken as third node. So now you take the difference in the coordinates of this node, difference in the coordinates of this node and this node. Then you are going to get a vector which is lying in the plane, in this plane, in the plane 1, 4, 2. A vector lying in the plane 1, 2, 4 is given by, if I take a difference between this, the coordinates of this node 1 and coordinates of this node, this is node 3. This is this global node number, but locally we are calling it as node 3. Okay, then I get a vector which is lying in this plane, vector lying in this plane. Okay, and then cross product of it. So vector lying in this plane, vector lying in this plane, cross product of that with vector lying along local x-axis is going to give you this one. So that is what this one. This is vector lying in 1, 2, 4 plane or 1, 4, 2 plane, and cross product of it with the unit vector along, or the vector lying along local x direction, that is going to give you y. And this y is a vector. Okay, this y is vector. It's not a unit vector. You need to normalize it. So that is how you got this y. And I want unit vector, not y. The vector in the pointing in the y direction, local y direction. But I'm interested only in unit vector. So you normalize it by dividing with each of the components. 0 divided by length of this element. This divided by length of this element. And 0 divided by length of it. So length of this element, what is length of this element? You can see length is 240 inches, and if you convert into 240 inches, so you divide this. So ly is actually you can actually length. This is all in inches. This one, what is this? 240. Anyway, unit vector is nothing but you need to normalize this. You need to normalize in the sense this square plus this square plus this square, square root of that. Okay, you normalize this vector, you are going to get unit vector along y direction. So that normalizing factor is this one. The normalizing factor is denoted with Ly. Ly has no meaning. Actually, Ly is this diagonal. Ly, or you can say some vector pointing like this in this plane. So Ly may not have any physical meaning, but this is a vector, and if you want unit vector along that, you need to normalize this. So that normalization factor is denoted with Ly. So that is how you get unit vector along small y-axis, and components of it are going to be Ly, My, Ny. So now you got unit vector along small x-axis, unit vector along small x-axis, unit vector along small y-axis. You take cross product of these two vectors, you get unit vector along small z-axis. So that is how unit vector along small z-axis is applied. And normalize this vector, whatever vector, if you here unit vector along small x-axis is not used, vector is used. So you need to normalize it. If you normalize, you are going to get Lz, Mz, Nz. So once you have all this Lx, Mx, Nx, Ly, My, Ny, Lz, Mz, Nz, you can write the rotation matrix for this single element. And here it is explained. The same R can be applied using orientation angle approach with alpha is equal to pi. So you can cross check that. That's additional information. So you need to repeat this kind of exercise for each of these elements, for element 2 and element 3. So the idea of choosing the third node, is to identify unit vector lying along each of the local coordinate axes. So you need to repeat that kind of exercise for all the elements. Anyway, this is for first element. This is rotation matrix, and using this rotation matrix, you can write the transformation matrix. Okay, you can write the transformation matrix, and then this transformation matrix is going to be of dimension. Here, rotation matrix is 3 by 3. Transformation matrix is going to be 12 by 12. Whatever local stiffness is there, to multiply this with T transpose T, you are going to get the global stiffness of this element. And the fourth node is the common node. So in this 12 by 12, I don't need to note down the entire 12 by 12 global stiffness matrix, only corresponding to free node, or the node which is not restrained, that corresponds to the second node. So the bottom 6 by 6 quarter is what we need to take, and that is what is written here. This is nothing but reduced stiffness contribution from element 1 to the global reduced stiffness matrix, and corresponding degrees of freedom are noted here. And what is the equivalent load vector? You can see here, for this frame element, UDL is applied. So you can go to your fixed end moments and then reverse this sign. That is how you can get the UDL. And then corresponding locations you need to put it. And if you do that, you can cross check it, you get this. Okay, similar exercise you need to do for element 2, and also equivalent nodal vector, because on element 2 also you have the UDL applied. And similar exercise if you can do for element 3. There is no equivalent load vector for element 3 because there is no load applied on the vertical member. Once you have all this, you can solve the equation system, solve for the unknowns. Once you solve for unknowns, go to each of the element, and get the local degrees of freedom using this relation dl is equal to t transpose d, and then determine whatever quantities you want. Axial force, shear forces, moments, and you need to use sign conventions. Sign conventions for axial forces, local shear, local moment, and then draw the free body diagram. You can repeat this for all elements and draw the free body diagram for each of the element and check whether each of the element is in equilibrium or not. Okay. So what I suggest is you spend some time on this, understand all this, or at least understand this problem clearly. And if there are any questions, you need to cross check all the calculations and get a feel for it. How to calculate this direction cosines along each of the axes. That is one important thing that you have first you seen in this problem. So that one you need to familiarize yourself, and you get the rotation matrix for each of the elements and get the transformation matrix, and multiply the local stiffness matrix with transformation matrix. And please note that at this stage, whoever is doing using pen and paper, now you can realize you need to adopt some software like MATLAB or Mathematica to solve this problem. Even to solve this problem, you need to adopt, because to multiply even the reduced stiffness matrix, to multiply that kind of thing, you require to work on 6x6 matrix. Okay. And if you use MATLAB, it won't take much time. Actually, MATLAB is optimized. MATLAB is a commercial software optimized. The name itself is saying it is good for matrix analysis. MATLAB is good for matrix analysis. Anything you want, you put it in matrix and vector form, and MATLAB is very useful to do those calculations. So it is optimized. That software is optimized for doing such kind of calculations. So you make use of MATLAB and then try to solve this problem, reproduce these results, and if any understanding problem, or if you observe any difference between your values that you got and the values that are given here, you please see, and then we can discuss further. But other than that, I cannot explain more than this unless you do put some effort. Okay. And then complete assignment 4 in all respects. Now you are ready to solve assignment 4 completely. Okay. Any questions here? Any questions? So the next topic is going to be whatever we learned. We learned two node bar element. Okay, beam element. We learned this to understand the bending effects and corresponding element. To capture the bending effects, we developed two node beam element. But the concept, whatever the concept we have gone through for developing the shape functions, even though we developed only two node beam element, if somebody is interested to get three node beam element, they can follow the same concepts and then derive three node beam element and corresponding equations. Okay. And after that, we looked at how application of this bar element, beam element for solving plane frame, plane truss, space truss, plane frame, space frame. Now we go back to bar element. or two-node element, two-node one-dimensional two-node element. And now, if I want more solution accuracy, or let me put it in another way, two-node element, two-node one-dimensional two-node element or bar element is also called constant strain element. Is also called constant strain element because it's a two-node element. The variable is going to have linear variation. If you take derivative of that, it's going to be constant. So it's also called constant strain element. But for some problems, the strain variation may not be constant. Okay, strain variation may not be constant in such cases. Or if you want more accurate, capturing strain more accurately, you need to go for higher elements, higher order elements. Instead of two-node element, we need to go for three-node or four-node element. Sometimes, if you see our failure function, it involves derivatives of stresses and derivatives of strains. So, in such cases, suppose if you are interested in plotting the gradient of stress and gradient of strain, we require to adopt higher order elements. So, we will see how to develop higher order elements. And by taking a general boundary value problem. So far we looked at a specific problem. What we looked at specific problem? Bar subjected to axial deformation or beam subjected to bending effects. So that is what we have studied. But now, if I want, because whatever finite element we are learning, it's a general tool which can be applied for any problem. So instead of focusing on specific problems, if we derive a general equation, element equation system for a general problem, depending on the specific problem requirements, we can identify and then get the element equations. So that is the idea of this general one-dimensional boundary value problem. And what is how we get the element equations and what is its applications we are going to see. And in this process, we also learn how to develop higher order elements. Okay, in this process we also see how we develop higher order elements. Maybe that is in the next chapter. Here, as far as this general boundary value problem is concerned, we will go in detail. Don't worry about it, even though I'm showing you slides quickly. Taking two-node element for general boundary value problem, how to develop the element equations. And then if you see specific case, because here there are students from other branches, aerospace, metallurgy and other branches. So the whatever finite element knowledge you are gaining, you should also see the application of it, not necessarily for structural engineering related, but it can be applied for any other field. Okay. So here, once we develop the element equation for a general boundary value problem, you can apply that for one-dimensional heat flow problem. Only thing is you need to compare how this differential equation is going to look like with a general boundary value problem differential equation, and then get the corresponding quantities, get the element equations for this kind of problem, and also that is conduction alone, and this is conduction convection. I'm going to quickly show you this. Okay, so for completeness, so you should not be of impression whatever you learned finite element is applied only for structural engineering problems or structural mechanics problems. And heat flow through thin films. Okay, thin films, such problems also you can apply, and lubrication problem you can apply. And also coming back to our structural mechanics, column buckling. Same general boundary value problem you can apply to this column buckling problem. So you will see all these applications in the next classes. Okay. And any questions? Any questions? It's surprising there are no questions. Either it should be very clear or nothing is clear. Anyway, if you have any questions, please send those things, or you can ask me. We can have a discussion. Okay, if there are no questions, let's meet in tomorrow's class.